Okay, in a vacuum, meaning no air, all radiation will move at the speed of light. And the speed of light is represented by the letter C. C stands for speed of light, and it's 3 times 10 to the 8th meters per second. Now, if you go on your equation sheet, you should see that the speed of light is given, meaning it's a constant. Now, I know that I wrote 3 times 10 to the 8th meters per second, and they put 2.998. It doesn't matter, okay? It's not a big deal. But the point is that this C, or this speed of light, is a constant, so you'll always know it. You don't even have to memorize it, all right? So we're going to first focus on light as a wave. So peak to peak is considered wavelength. This is the Greek symbol lambda. Okay, it's like this TP looking thing, or upside down Y if you want to look at it. And it's the difference between peak to peak, or right, this bottom part is called a trough, or trough to trough. And then how tall the wave is called its amplitude. And then how fast it travels, we're going to measure in meters per second. Now, this is like the metric system, right? Like how fast or the speed you travel in your car, we measure in miles per hour. But that's just because it's the English system. So we're not doing that. We're going to measure how fast something travels at the using the metric system and using meters per second. Okay, now again, here's what wavelength, this is its symbol. And then this is a new metric system conversion. So you'll see wavelengths in this chapter often or sometimes referred to in nanometers. And a nano is small, so 1 meter is 10 to the 9th nanometers. So someone will always ask me, well, can I do this? 10 to the negative 9th meters is 1 nanometer. Well, sure. This is the same thing. Okay, it doesn't matter, but I'm going to use this one because that's what I prefer. All right. Frequency is this Greek symbol nu, and it pretty much just looks like a V. All right. And it's how frequently you're seeing the wave per second. Okay. And the relationship between wavelength and frequency is an inverse relationship. So what does inverse mean? Well, when one thing gets bigger, the other thing gets smaller. So I'm going to just draw out I'm going to do my best to draw out 2 different waves. So like here's one wave. Okay. And then, of course, it's lagging. Wow. Shoot. Okay. So in the same amount of time, so like this is a certain amount of time that we see the wave. So you'll notice that this is a big wavelength, so higher wavelength relative to the one below it, okay? And you also see the wave less frequently. Look, you only saw the wave 1, 2, 3 times. So that means a low frequency. This is by definition what an inverse relationship is. Now look at this wavelength. This is a much smaller wavelength, shorter wavelength, so smaller wavelength, okay? And then because of the smaller wavelength, in the same amount of time, we see the wave 1, 2, 3, 4, 5, 6 6 times. So that's a bigger increase in frequency. So again, an inverse relationship. And so this is the relationship between the speed of light, c, which is given, right? It's a constant, and wavelength and frequency. So we're going to do some math with it. But first we're going to look at this spectrum. Now this spectrum is called the electromagnetic radiation spectrum. If you notice that at the top of it, you see wavelengths appear, and they're just by powers of 10. So this is a big wavelength, and this is a small wavelength. So it's kind of going like this. Okay. So you'll notice you've got these this is low energy waves down here. They're very large. None of these waves are harmful to us. However, after you get past visible light, all of these forms of radiation are harmful to us. Okay? That's because they're really high frequency and high energy waves. And then this little region in here, this big little tiny region right here, is of all of the types of light, radio, microwaves, infrared, all of these different types of light, this is the only portion we can see. So in the grand scheme of all of the different forms and wavelengths of light, we can only see this little tiny portion. So we're kind of like blind. Wow. We're kind of blind in the grand scheme of how much we can actually see with the naked eye. And this visible light is broken up into the different colors of the rainbow. You've got your red light down here, 750 nanometers. This is larger wavelength. And then the shortest wavelength of light is violet, which means your red light has the lowest energy of all of the colors of light, and the violet light has the highest energy of all of the colors of light that we can see. All right? So this is just a different chart that's flipped backwards. So you got your radio waves, kind of, right? These are calm, they're chill, and then they get like kind of crazy. So like super dangerous, high energy, high frequency, very, very low energy, not dangerous. We're exposed to these radio waves and microwaves every day, all right? So this is just a different electromagnetic spectrum. And again, we have this very tiny region of all of the spectrum that we can see. The rest of it we cannot see with our eyes. So if you didn't already know all the colors of the rainbow, I need you to know them now. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, not purple, all right? So you need to know that order. This is like the acronym that they use frequently. And we're going to just compare two waves and kind of see if we understand the chart and the concepts. So just based on A and B, which wave has the higher frequency? So which wave are you seeing more frequently? A or B?
A.
A. Good. Look at how often you see the wave. Short wavelength, high frequency. Now, for this one, I'd likely give you a spectrum, okay? Which wave would represent visible light and which would represent infrared? So you go, okay, well, let's look at our spectrum. So infrared is right here, and visible light is right here. So these are my long wavelengths, and these are my short wavelengths. So infrared has a little bit longer wavelength than visible light. So then who is who? Well, that would make B be infrared and A be visible light relative to one another. All right? Now, which one is red and which one is blue? Well, what did I tell you about red light? It's the lowest energy color of light. Which one of these represents a lower energy? Now, you actually don't know this mathematically yet, but you will in a second. Like, which one is more relaxed and which one is not? So lower energy is going to be B, so this would be red, and the higher energy is going to be A, and this is going to be blue. Bigger wavelength for red, shorter wavelength for blue. So red has the longest wavelength of all of the colors, and violet has the shortest wavelength of all of the colors. Any questions so far? All right. So let's do some math. It says a certain color light has a wavelength of 413 nanometers. So I give you wavelength. Okay, it says, what is the frequency? And you go, okay, well, which variable is frequency? Well, frequency, sorry, I unplugged. Okay, frequency is V, right? And I have an equation that has both of these in it. It is this one. C equals wavelength times frequency. And you go, okay, I'm solving for frequency, so that's this guy. So C over wavelength is frequency. Well, what is C? C is the speed of light, and it is a set number. Do you guys remember what it is? Your equation sheet, look it up. It's 3 times 10 to the 8th meters per second. Your equation sheet says 2.998, whatever. So C, speed of light, divided by wavelength. Now, there's a problem. Does anybody see what it is? I gave you wavelength in nanometers. What is the measurement and speed of light. It is meters. So you must convert nanometers to meters. Now, I really would like you guys to practice this in your calculator. The reason is I get a lot of calculator issues on this conversion, and it's usually the power of 10 that's off. So I just gave you this new metric conversion, 10 to the 9th nanometers in 1 meter. 4.13 times 10 to the negative 7th meters. So I'm going to give you a second because I want you to practice that in your this part right here, this 413 divided by 10 to the 9th. For me, if it was my calculator, I would hit 413, and then I'd hit the divide button, and then I'd hit the 10 to the x button, and then I'd hit 9. That avoids any issues with having I can't even think with any sort of exponent issues. So did you guys get this power of 10? Okay, so now be careful. So you take and do the math. 3 times 10 to the 8th divided by 4.13 times 10 to the negative 7th. So you take the math. You get rid of meters. Now be careful. This is meters over seconds. So your answer is 1 over seconds. Or you could write it as s to the minus 1 because these are equivalent. And this is also known in the frequency world as a hertz. Okay? Any questions on the answer, the 7.26 times 10 to the 14th, before I keep going?
I don't know how, but I just keep getting 7.26, but not the 10 to the 14th.
Did you read your whole calculator? And did you put this as a negative 7?
Yeah.
At the end of class, let me look at your calculator, okay?
Okay.
Okay, so then it says what color is it? Now this is where an electromagnetic radiation spectrum is going to come in handy. So the wavelength is 413 nanometers. So I'm going to pull up my spectrum and I go, okay, look at your colors down here. 750, 413 is definitely down here, right? So it's probably violet, right? 413 is very close to the end, so it's very, very likely that this is violet light. So a spectrum would be needed for that question. Questions on this problem? Besides maybe a calculator issue that we can fix in a little bit? We'll do more, so we'll see maybe, Skylar, if we figure it out along the way. Okay, so then there became a problem, and the problem was that, yes, energy can travel like waves. Electrons can move in wave-like format, but this didn't explain how an object can glow when it gets hotter, when its electrons get excited. So light as particles. So what they did is they used a device called a spectroscope, and the spectroscope has something in it where it like breaks up all of the colors of light. So it's kind of like a prism, right? And it was found that different elements gave off different forms of electromagnetic radiation when you heated them up. And because they weren't a continuous form of radiation, they realized that electrons can be emitted in what are called discrete packets of energy, often referred to as quanta, and that every single element gave off a unique pattern, okay? It's specific to its element. It's like its own little fingerprint, okay? So what happened is we've got this Bohr model of the atom. Now I kind of had cheated, right? Because I had taught you this first on like sort of like a shortcut way. So once Rutherford discovered the nucleus, Niels Bohr kind of put together this model of the atom where the nucleus was in the middle and that there were these sort of rings of electrons around, like circling around the nucleus, kind of like the planets move around the sun, all right? And they did sometimes call this like the solar system model. Now, he found out, and I'm going to just do hydrogen, okay? How many electrons does neutral hydrogen have? Well, 1, right? Because it has 1 proton. So they found out when they heated these elements, heating them means adding energy, right? And then if you add energy, these electrons, what they do is they get promoted to higher energy levels. And when I say these electrons, I mean this one electron, okay? So let's just say this one electron, I'll do this like this, started here. This is where it would be originally in its ground state. It'd be in the first energy level. And you heat it up and it's like, oh, it gets excited and it jumps up here. Well, now it's no longer here. It's in what's called an excited state. And the problem with electrons in excited states is they're not very stable up there. So they absorb this energy from heating them. You can also do this by supplying electricity. Electricity is another source of energy, okay? And so you excite them, right? And then they're like super unstable. So what do? Well, they eventually will fall back down to their ground state where they originally came from, wherever that may be, okay? Well, in law of conservation of energy is neither created nor destroyed. So where does the energy go that it absorbed to begin with? Well, it comes out. It's released, it's given off, and it's given off in the forms of radiation. And now if the radiation is in the visible region, they were able to see it using a spectroscope, okay? So these things were glowing, and so they took a spectroscope and like it looks with our eyes continuous, right? It looks like one color, but if you look through a spectroscope, you can split the color up and see that there were unique different sets of colors or wavelengths or packets of energy being released, right? Because light has energy, violet light has a certain energy, red light has a certain energy. And the coolest thing was that these lines were unique. So this was everything I just said, okay? Going up from its ground state by absorbing energy and then releasing energy by falling back down. So up to excited state and then falling back down and releasing energy. And when it releases the energy, if it's in the visible region, us as humans can see it. So check this out. This meant, right, that we had determined that light or electrons or energy, right, could be moving around like a wave, right? Well, now they were seeing distinct energies, like they used a spectroscope to look at something that looked like a continuous color, and they noticed that that color was broken apart into different discrete colors. Okay, this is a specific energy. 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 They weren't like this continuous, like red, orange, yellow. They weren't seeing a continuous rainbow, is what I'm saying. And if they're not seeing a continuous rainbow, it means that there are set amounts of energy where they were seeing the specific, they're going to end up calling spectral lines. So what that means was around the nucleus of the atom, there were set energy levels. And that's where the Bohr model came from, was that like an electron can be here or here or here, but it can't be anywhere in between. So electrons weren't in this like continuous glow around the nucleus. They were on these discrete energy levels, kind of like a ladder. When you go to walk up a ladder, okay, you got to put energy in to walk up the ladder, right? But you can't step in between steps. You're either on the first step or you're on the second step, but you're not anywhere in here. And so what they found by seeing these unique energies is that these electrons were on unique, what they called energy levels or shells. Okay, now look, I'm going to skip this and I'll come back to it in a second. Look at hydrogen's emission line. This is called its emission spectrum. These are called spectral lines. So you see a very distinct line that is like super violet, okay? And then there's one that's kind of like a little bit more purple. And then there's one that looks kind of like indigo. And then this one is kind of like a blue-green right here, right? And this one is red. And then this is it. These were the only energies of light. So there was this energy and this energy and this energy and this energy and this energy that we could see with our eyes. Okay, so the Balmer series is what we can see with our eyes. That there were discrete energies of light being emitted or given off by a hydrogen atom when heated. All right. Now, the whole idea was that we originally thought light or electrons moved only in a wave. Well, if that was true, you would see all the colors of the rainbow, right? You would see this perfectly continuous color of the rainbow, and they don't. They're seeing this energy, this energy, this energy, this energy, this energy. There aren't even any orange or yellows hydrogen's giving off. Okay, they don't even have those colors. So there were unique sets of energies that hydrogen's given off. And so what they learned is, as they looked at all the different elements, is that every single element has its own unique spectral lines, meaning every single element has its own unique electron configuration around the nucleus, so it gives off a different emission spectrum than any other element. So these spectrum emissions, these emission spectrums, are kind of like every single element's fingerprint. It's unique to that element. So no other element in nature looks like this, because no other element in nature has the same arrangement of electrons that hydrogen has. Hydrogen's arrangement of electrons are different than helium's, and helium's are different than argon's, and argon's are different than zinc's, and zinc's is different than platinum's, and so forth. So let's look back. Look at neon's. Neon has tons of spectral lines. Now, it doesn't have every single spectral line, but look at all of these lines that are given off by neon. It looks totally different than hydrogen's. And that is because neon has a different arrangement of its 10 electrons as opposed to hydrogen that only has 1. And so it gives off its own unique pattern of spectral lines. But again, this gave the idea that light doesn't only travel in a continuous pattern, right? These are distinct energies of color. They're not a full continuous color. And that is unique to each element because each element has a unique arrangement of electrons around its nucleus. So this is different from a rainbow. I need this to be very clear. A rainbow is the reflection of light on water particles. That has nothing to do with electrons in an atom being excited and releasing unique sets of energy. They're totally not the same thing. Okay. However, I do want to bring up a point what do scientists what do scientists use in where is this like a real life application? Anybody know? Not the rainbows, but like where is it a real life application where scientists are trying to figure out what elements are made up of something? Like, anybody know? I'll give you a hint. What about astronomy? Scientists are constantly trying to discover what in astronomy? Anyone? How about like what different stars and things like that are composed of, right? They want to know are they made of hydrogen? Are they made of helium? What's in there, right? This is how they figure that out, because they can look at them and figure out what sort of emissions are being given off and say, okay, it looks like this star is composed mostly of helium or has a lot of helium in it based on its emission spectrum. So this is obviously done on a way bigger scale, but it is this concept of being able to identify the composition of things in astronomy. This concept comes into play because every single element has its own unique series of spectral lines. And obviously their tools are a lot more sophisticated, but it does play an important role in astronomy. Okay. So because we discovered light can behave like a particle instead of a wave, and I shouldn't say instead of, in addition to a wave, we can't use the wavelength equation for all particles. We also have now an energy equation for light as particles. So light can behave like a wave, but it can also behave like a particle. And now we can quantize the energy. I mean, we can find out how much energy each particle of light has. And here's the equation for it. If you look on your equation sheet, oopsies, it is right here, E equals hv, where h is a constant, just like c was. So again, you don't have to memorize it. It is this number, 6.626 times 10 to the negative 34th joules per second. And because of that, we can figure out how much energy each photon or particle of light has. Okay? Now, notice that this also has frequency in it, just like the other equation did. So we're going to do some math. It says a certain electromagnetic radiation was found to have a wavelength of 30 meters. What is the frequency? Well, we just did this before, right? C equals wavelength times frequency. Oops. I thought I had an extra slide in there. So C equals wavelength times frequency. I give you wavelength. I want frequency. That's this equation. You always have C. It's the speed of light. So C over wavelength is frequency. So what's C? C is a constant. It is the speed of light. It is this number, 3 times 10 to the 8th, meters per second. Divided by wavelength. Well, now they gave you wavelength in meters, which is nice because that's what our speed of light is. So 30 meters. I don't have to do any like conversions. So meters cancel, and you end up with 1 times 10 to the 7th, 1 over seconds, or hertz, or s to the minus 1. I'll give you a second to calculate it out. Okay, so the next question, so we have frequency, and now we want to know energy. Well, I just taught you that there's an equation that has energy in it. It's E for energy equals H, which is called Planck's constant, times frequency. Well, I just solved for frequency in the first part. So you take that number and plug it in here. So E equals, H is Planck's constant. You can look it up on your equation sheet. It's this number. And frequency, I just solved for. It's this number. 1 times 10 to the 7th. I'm going to write it as 1 over s so I can show you how units cancel. Look at seconds. And you calculate it and you get 7 times 10 to the 27th joules, and then I just need you to write per photon. All of these energy this energy equation is always per photon, or for 1 particle of light. 1 particle of light. How we doing? Okay, I'm going to do something else on here in a minute, but first it says, what type of radiation is this? So at this point you would need an electromagnetic radiation spectrum. So you can either use the wavelength or the frequency, depending on what your chart has. So here's my wavelength. Here's my frequency. So if you notice, if you refer to an electromagnetic radiation spectrum chart, that the frequencies and the wavelengths are only in powers of 10. So what that means is this coefficient out front is irrelevant. You're just going to focus on the power of 10. Now, I didn't write wavelength in scientific notation. I could, right? 3.0 is the same thing as 30, is the same as 3 times 10 to the 1. So again, we're just focusing on the power of 10. So 10 to the 1 is where I would look for wavelength. Or I have frequency, so again, you're just focusing on the power of 10. I'd find 10 to the 7th. So let's check it out. Wavelength 10 to the 1. That sure looks like it is right here. Radio waves. Now, I said you could have done frequency, right, which is down here. Frequency is 10 to the 7th. Well, okay, right, the same spot. It shouldn't be, if you pick one or the other, they should fall in the same spot, right? Because they're proportional to one another. So again, this would be radio waves. If I asked you this type of question, this last part on a test, like what type of radiation is it, I would give you this spectrum. There's no way I need you to memorize this, okay? So, something that they do, I'll do it right here, that they do often ask, or that they can ask, oops. That was our answer for energy, right? Something that they can ask, right? So remember when we talked about like Avogadro's number and everything like that, and that one molecule or one atom is like super duper duper small. So scientists came up with this unit of the mole to talk about like molecules and atoms in bigger like forms. So that's the same thing with like a particle of light. This is like one little itty bitty teeny particle or photon of light. So what they can also ask you for is they could ask you for how many is it per moles of photons, because moles are a little bit easier to talk about because you're talking about more things. So how would you do that? Well, 1 mole of anything is what? 1 mole of anything is what? How many of that thing? Woohoo! It's been a while. Good job. Avogadro's number, right? 6.02 times 10 to the 23rd. 1 mole of photons is 6.02 times 10 to the 23rd photons. So how would you convert this? Well, you would go, okay, photons on the bottom, so photons on top. So 6.02 times 10 to the 23rd photons for every 1 mole of photons. And now you would have joules per mole of photons, okay? So they can extend it to have you convert it to joules per mole. So I just kind of wanted to pass that along. All right, so this question says, calculate the energy of yellow light with a wavelength of 589 nanometers. Now, they give you wavelength, and they ask for energy. There are 2 ways to do this. I'm going to show you the way that I'm not going to do it first, but I do want to show you a manipulation because there's no equation right now that has wavelength and energy in it. We have 2 equations. They are this. Speed of light equals wavelength times frequency, and energy equals Planck's constant times frequency. We have these 2 equations. Neither of them have both of these variables in them. But both of these equations have which variable in common? Frequency, right? So I'm going to manipulate my speed of light equation. C over wavelength is frequency. And then what I'm going to do is I'm going to take this and now plug it in for frequency here. So I can write the energy equation in terms of wavelength. So E equals H, and then it's C over wavelength. But I'm not expecting you to be able to do this on a test, because if you look at your equation sheet, this is not on there. So this would require you to do this yourself, and I'm not going to expect you to do it yourself, though you can if you want to. However, I'm going to show you how we just did it the last time. If you know wavelength, you know this guy, and you already know C because it's the speed of light, you can solve for frequency, and then you can plug the number in down here. And that is the way I'm going to choose to do it. Now, you need to be careful. Your wavelength is in nanometers. So 589 nanometers, 10 to the 9th nanometers in 1 meter. So you can do that, and you should get 5.89 times 10 to the negative 7. And then C equals wavelength times frequency. So C over wavelength is frequency. C is the speed of light. It is this number always, 3 times 10 to the 8th meters per second, divided by wavelength is 5.89 times 10 to the negative 7th meters. My meters cancel, and I'm left with 1 over seconds. Be very careful. That seconds is in the bottom. I'm going to pause for a minute and let you work this out because I want to know the frequency, please. The frequency. Okay. And then you're left with joules per, you have to just kind of include the photon yourself, per photon. So you get the frequency from the speed of light equation and then plug it into the frequency in the E equation because both of those equations have frequency in common. Any questions before we move on? So the constant speed of light, well, first of all, that's only in a vacuum. So the constant speed of light is just how fast it's moving in a vacuum, and the frequency is how frequently you see the wave per amount of time. So if they move at the speed of light, but you're seeing the wave more frequently, you will see more waves in that amount of time. Okay, so FRQ 1999. All right, we're going to do the three parts of A and just the first part of B. So I'm going to pause this in a second, and I want you to do A, 1, and 2. Please, just do A, 1, and 2. This is just what we've been doing. So here's what's interesting. You can take atoms or molecules or ions or whatever, and you can take them and you can, obviously there's special machines and things to do this in, and you can shoot certain forms of radiation at them. So look at this. You can shoot a color of light. So 495, what's that? I don't know. Let's look. Let's look on our spectrum. Where's 495? That's like about here. So it's probably like greenish light, right? So you can shoot green light at chlorine gas, and that green light has enough energy to break the bond, meaning you can rip the chlorine atoms apart, or the chlorine molecule, I should say, apart. So that is a way that they can break bonds, by shooting certain like colors of light or certain forms of energy, because light has energy. So again, they give you the wavelength, you're going to calculate frequency, and then you're going to calculate energy. So I want you to do that on your own. That's everything that we've been doing. Okay, so I'm going to write that number up here. 6.06 times 10 to the 14th. And again, you can write this as hertz or 1 over seconds or s to the minus 1. I'll just write it as 1 over seconds, okay? It doesn't matter. However you choose, I will accept any of these 3 units for frequency. And then calculate the energy. Well, once you know part 1, you just plug into the energy equation. E equals hv for part 2. This would be, just kind of as an example, an opportunity for double jeopardy. Let's say you calculate part 1 wrong. Maybe you didn't know how to do it, or you punched something in your calculator wrong and this number comes out wrong. Well, if you do part 1 wrong, but you use your number correctly, in the correct format in part 2, you have the potential to get full credit on part 2 as double jeopardy points. So did anybody have the E or energy? I can't remember from last class, sorry. So we take our energy, we turn it into kilojoules using the metric system, and we use Avogadro's number to turn it to kilojoules per mole. So if this is how much kilojoules per mole of photons the light has, that's how much energy must be stored in the bonds. Because if it takes 50 kilojoules of energy to break the bond, that means the bond must have had 50 kilojoules of energy stored in it. Andy, it might just be a calculator thing. Or rounding. I wouldn't worry too much about it. That would be a completely acceptable answer. Don't worry too much about it. What does this number come out to be? Anybody have it? $242? Okay. So that means the chlorine-chlorine bond is considered to have 242 kilojoules per mole of energy stored in it. So this is how much energy you have to throw at it if you want to break it. So that bond has this much energy in it. Remember bond energies? So they're shooting light at it to break it, because light has energy and energy can break bonds. But that light better have at least this much energy or it won't be able to rip the molecule apart. All right, I'm skipping for the sake of time, and we're going to go here. So this is these are two videos you can watch for review and maybe better understanding. And the important ideas from the Bohr model, which is like that solar system model, and the important points that is still true today is that electrons can only exist at certain energies away from the nucleus, these discrete energies. They're either on one ring, and really they're not rings, but they're on one energy level or another. They aren't like in between rings, and they can transition from one thing to another by absorbing and releasing energy. Okay, so the quantum mechanical model, though, is the model that we use today, because the atom is actually a little bit more, or a lot more complicated than just throwing electrons on these rings. So sorry, I just skipped this. The Bohr model, his model of the nitrogen atom would have been this. Okay, nitrogen has 5 electrons, and so 1, 2 on the first ring, 3, 4, 5, and then he thought they just like orbited in these rings. Now he was right in the sense that these electrons were like on discrete energies away from the nucleus, energy levels or shells away from the nucleus, but they weren't in this beautiful like perfect orbit around the nucleus. Okay. The reason that became an issue was because it's virtually impossible to know where an electron is at any given moment, because they're constantly moving. Okay, so the Schrodinger wave equation is very, very complicated Calc 2 material, but the whole idea behind it was that you could find out these probable locations you are likely to find electrons around an atom at any given moment, and they named these things orbitals. Okay, but it is a lot more complicated than just these rings. Now, we're going to use the rings a lot of times for simplicity's sake, because we want to talk about how electrons are moving from one energy level to another, so it helps us describe that generally. But the atom is a lot more complicated than just these little like rings around the nucleus. It, in fact, looks more like this. So you have these orbitals, or these regions, where they're consistently finding electrons around an atom over a given period of time, okay? And they're not just these orbits, they're these complicated looking shapes, all right? So now is where I need you to have you reference your periodic table. I need you to just listen very, very, very closely, okay? So your alkali and alkaline earth metals are known as your s orbital elements, or s block. Okay, now I realize helium is over here, but it is an s block element. All right, it's on the first row. Now boron, over this whole family over here, this whole, well, it's not a family, this whole group over here are p orbitals, or your p block elements. All of your transition metals are called d orbitals, or d block elements, and all of your lanthanides and actinides are considered f block elements. Okay, so the periodic table can be read like a book. So I'm going to pull up my periodic table, and I'm going to read this to you like a book. So now is where I really need you to pay close attention, right? So these were considered S, right? These, with the exception of helium, are considered P elements, P block elements, okay? All of these guys are D block elements. And then you got your lanthanides and your actinides that are F block elements, okay? So S, P, oh, whoa, what? P, D, F. Are we good? Good so far? So again, this is going to take practice. So listen, I just need you to pay very close attention as I'm walking you through this. We are going to read the periodic table by the book. What I mean by that is we're going to read what energy level we're on. That's going to be called N. That's our principal quantum number. What block we're in. So S, P, D, or F. Okay, and I'm going to read it like a book. So let's start at hydrogen. Hydrogen's our first element. We're reading it like a book, left to right, top to bottom. So hydrogen's our first element. What energy level is it on? Oops, I'm going to change my color. I want the color to change. So having said that, though, what energy level is hydrogen on? 1, is that right? Why? It's in the first row. That's why. What block is this? Hydrogen and helium are, I know that this looks like it's in the P block, but it is not. These are S block elements, 1s. Until helium. What row are we on next? What row is this? 2. What block is this right here? These two elements. They're in the S block, right? Okay, keep reading. I got to keep going. I got to keep reading my periodic table. What row am I in? I'm still in the second row. 2. What block is this though? This is my P block. Until I get to neon. And then I jump down. What row am I in? Now I'm in the third row. What block is this? That's the S block. Keep going. Till I get to here. I'm still in the third row. What block is this now though? This is the P block now. Keep going. I'm at 4. What block is this? S. Okay, now this is where it gets tricky. I need everybody to pay very close attention and you'll learn why this is later. But this D block starts on the third energy level. D orbitals begin on the third energy level. And I do realize that they are lined up in the fourth row, but this entire row right here of D block elements are not called 4D. They are called 3D, and I just need you to know that. So 3D is next. And then we go back to normal, where we're at, what's after 3D? We're at gallium, right? It's normal now. So this is 4, we're back to normal. And then again, we're in the P block. So then what's next? 5, right? 5th energy level. These are S block elements. Now keep reading. If this first D block row is called 3D, what is the next one called? I will wait for you to answer me. If the first one is 3D, what's the next one called? 4D. Good job, guys. Good job. 4D. And so it goes on and on and on, and we'll talk more about this next week. But this is the order that we fill electrons in around the nucleus of the atom, because these guys are orbitals, okay? And let's talk about what these orbitals are like. So N is your principal quantum number. You used to have to know all of these. N means what energy level you're on. Are you on the first row? Are you on the second row? Are you on the third row? Are you on the fourth row? Okay, so like AKA what ring you're on. N equals 1, N equals 2, N equals 3. Now I know the ring is not the best model, but I'm just using it to try to help visualize. N equals 4, okay? So for here, this right here is N equals 1. N equals 2, N equals 3, N equals 4, N equals 5. Notice it only goes to 7, yeah? Okay. So this is the only number this is the only quantum number you're responsible for. Now, L technically stands for which orbital, aka SPDF. So you have to know SPDF, but there's certain numbers that go with them that you don't have to know. So, first type of orbitals are our S orbitals. How do I know? Well, go look at your periodic table. The first element on the periodic table, I'm going to close this because it is an absolute disaster right now. The first element on the periodic table is hydrogen, and the first block on the periodic table is the S block. So my S orbitals, right, we said the S orbitals were right, this whole family right here. My S orbitals start on this first energy level because this is 1s right here. All right, and s orbitals are spherical in shape. So what, and there's such thing as a 1s, a 2s, a 3s. There's only one shape because a sphere is a sphere is a sphere, okay, no matter how many axes you rotate it on. So in real life, what they've done is they've looked at an atom that has what they consider, and what they ended up calling an s orbital, for s for spherical, okay, and This right here is a real life electron density diagram, meaning they were able to map the electrons over a long period of time, and at any given moment the electrons sure looked like they were in some sort of spherical looking shape right here. So that's why they called s orbitals spherical. This is a real life model of electrons over a given period of time. You had a very, very good chance of finding electrons in this type of region for s orbitals. Now p orbitals, so then again, this would be like a 1s, this would be like a 2s, 3s. Look at that. This is a real data from an s orbital. All right. Now p orbitals are more complicated. Now they don't start till the second energy level, and you go, well, why? So what time does the bell ring? 9, right? P orbitals, this is where my p block starts, right? What energy level is it on? 2. So p orbitals do not start until the second energy level. And there are 3 different shapes. Now this is kind of a lie. There aren't really 3 different shapes. They are the same shape rotated around different axes. It's a dumbbell shape. Okay, it's the same exact shape, dumbbell, 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 just rotated along 3 different axes, right? Because we live in 3 dimensions. So 1, 2, 3 shapes, or 3 orbitals for the p orbitals. Okay. And then look, this is a real life electron density diagram of a p orbital. Over a given time, look at, this is where they were finding electrons most of the time, the most probable regions. Okay, D's get kind of super complicated. They look like 4-leaf clovers, except for this one. So D has 5 different orbitals, or 5 different shapes. And now remember, your D block does not start till the 3rd energy level. So that's right here. Remember, we call this 3D. I realize it lines up with the 4th row, but we call this 3D. So those electrons are really on the 3rd ring, or 3rd energy level, if you want to think about it that way. Okay, and then the f orbitals are even crazier. We haven't talked about f yet. We will next week, but they don't start till the 4th energy level. And then you've got these 3 funky looking orbitals, and then these 4 kind of 8-lobed, they kind of look like flowers, orbitals. So there's 7 orbitals, or 7 shapes for f orbitals. So what we're going to do now is we're going to organize electrons in the orbitals around the nucleus. So this is going to be called electron configuration, or orbital configuration. And there's some rules of how you do it. So I'm going to quickly go through the rules. I realize the bell might ring at 11:09. I need you to give me till 11:11, please. Please give me till 11:11 if you can. So there's the off-bow principle. So that's the fact that the electrons occupy the lowest energy level first. It's where they're easiest to go. They're not going to want to jump up to higher energy levels. They're going to go in where it's the easiest to go first. The next rule is that you can only put 2 electrons in an orbital. So they max out at 2 in each orbital. And if you do put them in an orbital, they're representing electrons with arrows. Now, I write electrons like this, and it doesn't matter how you write it, but these are my electrons. That's how I was taught. It's how I will do it. They have to have opposite spins, and the reason that is electrons don't like other electrons. So what prevents them from flying off the atom, if you have to put them next to each other, is them spinning opposite directions. Okay, and then this last rule is that because electrons repel other electrons, if there are multiple orbitals you can throw them in, they will spread themselves out first before they pair up, and that's known as Hund's rule. Okay, so here we go. We're going to start with orbital notation today. We're going to fill in the electrons into orbitals around the nucleus of an atom. And we're going to start with phosphorus. So phosphorus is atomic number 15. That means if it's neutral, it also has 15 electrons that we have to fill in around its nucleus. Now you can think of this like this. This is my first ring. So think of the nucleus like down here, okay? And I'm doing like a half of an atom. So like, you know how we do atoms like this? In this orbital, I'm kind of like cutting this in half. So I'm looking at it like this, okay? So there's like my first ring. These guys are in my second ring. These guys are in my third ring. Ooh, then it gets bigger, right? These guys are in my 4th ring, and so forth. All right? Now, it is my job to fill in 15 electrons. So I need to follow the rules because it's atomic number 15. So my 1s is my lowest energy level first. That's the off-bow principle. You got to put them in there. And they have to spin opposite directions if I'm going to shove them both in there. 1, 2 electrons. The next energy level is where you go, 3, 4. Now, Hund's rule, you spread them out until you're forced to pair them up. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I need 15, so I'm not finished. So keep going. 11, 12, 13, 14, 15. This is the orbital notation for phosphorus. So notice that they're not in these beautiful rings. They're in these kind of more complicated orbitals. Now, before you head out, I want to kind of go over why are there these numbers of boxes? Why does the S have one box? Why does the P have this? So look at your S. Every single S orbital, 1s, 2s, 3s, 4s, 5s, 6s, 7s, only has one box. Why? Why is there only one box? Well, because S orbitals only have one shape. It's a sphere. There's only one orbital for S orbitals. That's it, one orbital. Look at your P's, 2p, 3p, 4p, 5p, 6p. 3 blocks, 3 blocks, 3 blocks, 3 blocks, 3 blocks. Why do these P's have 3 boxes? Because P orbitals have 3 orbitals. Who are they? Px, Py, Pz. Okay? Look at all your D energy levels. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. All of your D's have 5 boxes because there are 5 orbitals. They have more complicated names. They're called like DXY, DYZ, DZY, or DZX, whatever. Anyways, there's 5 shapes or 5 orbitals. And then your F has 7 shapes or 7 orbitals, which is why there are 7 boxes available, because there's 7 different places around the atom that an electron could probably be found. Okay, so I'm going to end here for our notes, but I'm actually going to continue a little bit on your homework to add to this to help you guys start it. But again, now we're getting into arranging the electrons around the atom. And when you arrange them in these little boxes, also known as orbitals, it's called orbital notation. So your homework is to go over this, to do this. So I'm going to kind of start you off since we ended with just beginning to practice. I'm going to do the first, probably, I'll do like a couple random ones, and then I'm going to let you, you should be able to, get it by then. So when you do the orbital notation, you want to be filling in the number of electrons that each element has, right? So you find hydrogen on your periodic table. Hydrogen has 1 proton, so it has 1 electron. So you fill in 1 electron. That's it. 1 electron. So that's it for hydrogen. Now, this box down here is where you're supposed to write the electron configuration, which I haven't really gone over yet, but I am going to show you because I think with the orbital notation, it is not too difficult to do. So what you do is you write out what energy level it's on and what orbital it's in. So that would be the 1s. And then as an exponent, you put how many electrons are in that orbital. And there's 1 electron in that orbital. So hydrogen's electron configuration is called 1s1. Okay? So let's go to lithium. I'll skip helium for now. Lithium has 3 electrons, has 3 protons, so 3 electrons. So you can only put 2 in an orbital before you max out. So 1, 2. But I need 3, right? So I have to go to my next energy level, 3. Okay? So I have 3 electrons. So now when I write out the electron configuration, I write out 1s, and then there's 2 electrons in here. So I put a 2 up here. Now, I have to jump up, right? I have another energy level of electrons. So now I write out 2s, and there's 1 electron in here, 1. And so this is the electron configuration for lithium. So this part right here is the orbital notation, and this part right here is the electron configuration. Let's do nitrogen. So nitrogen, you go to your periodic table. It has what? Ooh, why am I blanking? 7 electrons, I think. My brain is not working. Pretty sure it's 7. Okay. So nitrogen. So you go 1, 2, 3, 4, 5, 6, 7. Remember, you don't pair them up until you have to. Okay? Now, we're going to write its electron configuration. So again, this is 1s, and there's 2 electrons in there. So that number goes up here. And then I go to the next one, so that's 2s, and then there's 2 electrons in there. And then I go to the next one, which is called 2p, and there are 2, 3 electrons. And so this is nitrogen's electron configuration. Now, as atoms get bigger and bigger and bigger, meaning they get more and more protons and therefore more and more electrons, it can get kind of harder. So I am going to take a moment and I'm going to do one of the harder ones. Let's see which one I'll do first. Actually, I think with this is enough. I'll do one more with you. I'm not going to do one of the harder ones. I think with this you can feel pretty good about what you're doing. So let's see. Silicon is atomic number 14. So we need to fill in 14 electrons. So again, you always start at the lowest energy level first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this is its orbital notation. So now I'm going to include its electron configuration in here. So again, first energy level, s orbital, and there's 2 electrons in there. Second energy level, s orbital, and there's 2 electrons in here. Still on the second energy level, but now we're in p orbitals, 2, 4, 6 electrons in there. Third energy level, s orbital, 1, 2 electrons. Still the third energy level, p orbital now, 2 electrons. Now, if you take all of your exponents, the 2, the 2, the 6, the 2, the 2, it should add up to the number of electrons because those should be electrons up there. So it should add up to 14. 2 and 2 is 4, plus 6 is 10, plus 2 is 12, plus 2 is 14. So that adds up to my 14 electrons that belong to silicon. So hopefully this helps. I know I didn't completely finish or do more practice, but I feel like you guys are probably able to watch this and figure this out on your own now at this point. Please let me know if you have any questions.